Welcome to Electronic Seed YouTube channel. Today in this video, we will learn about fault collapsing and fault dominance in DFT. Let's get started. As digital circuits become more complex, testing them becomes increasingly challenging. With greater circuit complexity, the number of possible faults increases rapidly. This growing fault count can make testing a major consumer of time and resources. At each node, I need to consider both stuck at 0 and stuck at 1 conditions. For every node, I have two possible stuck at fault conditions, 0 and 1. Trying to detect every fault can therefore require a very large number of test vectors. I can reduce that requirement systematically by applying fault collapsing. The goal is to remove redundant testing without reducing the faults I can cover. I reduce the number of tests by using equivalence and dominance relationships between faults. Equivalent faults behave identically during detection, so redundant ones can be removed. Dominated faults are already covered by the detection of another fault. Together, these methods make ATPG and manufacturing testing more efficient. First, I will look at why the fault testing problem becomes difficult. Next, I will study fault equivalence and how it applies to logic gates. Then, I will examine fault dominance through practical examples. After that, I will cover the checkpoint theorem and test optimization. Finally, I will compare testing approaches, discuss benefits, and summarize the key ideas. I consider every node in a combinational circuit as a possible location for a fault. A node is simply an interconnection point in the circuit where a fault can occur. These nodes include gate inputs, gate outputs, and branches created by fanout. With n nodes, I have two n possible single stuck-at faults. Each node can independently be forced to either logic 0 or logic 1. So every node contributes two different stuck-at conditions to the fault list. For n nodes, this gives a total of 2n single stuck-at faults. As the number of nodes grows, the amount of testing grows with it. Here I consider a simple circuit with 16 possible fault sites. Since each site has two stuck-at conditions, manual enumeration gives 32 faults. Without any reduction, I might need a separate test vector for every fault. That would create long test sequences and increase both manufacturing cost and testing time. I look for relationships between faults so that one vector can detect multiple faults. When faults are equivalent, I keep only one representative for testing. When a fault is dominated, I can remove it without sacrificing coverage. The result is a smaller test set that still provides complete fault coverage. Fault equivalence means F1 and F2 have exactly the same detection behavior. Every vector that detects F1 will also detect F2. The reverse is also true. Every vector detecting F2 detects F1. I can therefore group equivalent faults together and represent the group with one fault. From each equivalence class, I keep just one representative fault. The other faults in that class do not need separate consideration during test generation. Removing those redundant faults means fewer test vectors are needed. Coverage stays the same because detection works in both directions between equivalent faults. The equivalence relationship depends on the particular gate and the stuck-at value. For an AND gate, an input stuck at 0 has the same effect as an output stuck at 0. If one AND input is permanently 0, the output remains 0 regardless of the other input. That observable behavior is exactly the same as forcing the output to 0. For a NAND gate, an input stuck at 0 is equivalent to the output being stuck at 1. A 0 on any NAND input forces its output to 1. This opposite value results from the inversion built into the NAND function. So the corresponding output fault has the opposite stuck value. For an AND gate, an input stuck at 0 is equivalent to the output stuck at 0. For an OR gate, an input stuck at 1 is equivalent to the output stuck at 1. For a NAND gate, an input stuck at 0 is equivalent to the output stuck at 1. For a NOR gate, an input stuck at 1 is equivalent to the output stuck at 0. An inverter simply reverses the logic value from its input to its output. Therefore, an input stuck at 0 corresponds to an output stuck at 1. Similarly, an input stuck at 1 corresponds to an output stuck at 0. These equivalences directly follow from the inverter's logic inversion. I will use a 2-input AND gate with a single output as a simple example. There are 3 nodes, and each node can have 2 stuck-at faults, giving 6 total. The 2 input faults and the output fault are all stuck at 0. Because they are equivalent, those 3 faults can be represented by 1. Before collapsing, I need to consider all 6 possible faults. Equivalence lets me remove 2 redundant stuck at 0 faults. That leaves 4 representative faults in the reduced fault set. So the test vector requirement drops from 6 to 4. Fault dominance means that detecting one fault automatically covers another fault. The tests for the dominated fault form only a subset of the tests for the dominating fault. Because of this overlap, I can remove the dominated fault from consideration. Testing the dominating fault then provides coverage for both faults. I will examine 2 stuck-at-1 faults on an AND gate. F1 is located at one of the gate's inputs. F2 is located at the gate's output. By comparing how these faults are detected, I can establish their dominance relationship. F1 can only be detected when every other input is set to logic 1. The particular faulty input must be driven to logic 0. Under this condition, the faulty gate produces 0 when the expected output is 1. That same test vector also detects the output stuck-at-1 fault. F2 is detected whenever the correct circuit behavior would normally produce output 0. The test that detects F1 is included among these conditions. But F2 can also be detected by other vectors that do not detect F1. Therefore, the detection set for F1 is smaller, making F2 dominant. Since every test for F1 also detects F2, I identify F2 as the dominating fault. I can therefore remove F1 from the fault list. For an OR gate, the corresponding dominance relationship works in the opposite direction. Their input stuck-at-0 faults are dominated by the output stuck-at-0 fault. This table compares equivalence and dominance by their detection relationship, fault removal, test set impact, and order of application. The checkpoint theorem gives me a powerful way to optimize testing in combinational circuits. I generate tests that detect all single stuck-at faults at the selected checkpoints. Those checkpoint tests also detect the other possible stuck-at faults in the circuit. This gives another significant reduction in the amount of fault testing required. I do not have to create separate tests for every internal fault. Tests aimed at checkpoints can provide coverage across the rest of the circuit. This makes the fault collapsing process considerably simpler. I can concentrate test generation on the important circuit locations. A checkpoint is a selected circuit node used as a representative location for fault testing. One type of checkpoint is a primary input node. The other type is a fan-out branch. These selected locations become the basis for checkpoint-oriented test generation. A gate output that does not fan out is an example of a non-checkpoint node. Faults at these non-checkpoint locations are covered automatically by tests aimed at checkpoints. So I do not need separate tests for every internal node. This lets ATPG concentrate on the circuit locations that matter most. ATPG stands for Automatic Test Pattern Generation, which creates tests for detectable faults. ATPG tools use fault collapsing to create smaller and more efficient test sets. The first step is to enumerate all possible fault locations. After that, I progressively reduce the fault list before generating the final tests. First, I enumerate every possible fault location in the circuit. Next, I collapse equivalent faults and keep one representative from each class. Then, I remove faults that are dominated by other faults. Finally, I apply checkpoint optimization to reduce the list to checkpoint-based faults. After all these reductions, I am left with a much smaller fault set. I then generate test vectors specifically for those remaining representative faults. The vectors are targeted at the faults that remain after collapsing. The final test set maintains coverage while using fewer vectors. A smaller test set means less time is needed to apply the tests. Fewer tests also reduce the cost associated with manufacturing test. The reduced number of vectors means less test data needs to be stored and handled. A smaller fault set also allows ATPG to run faster. Fault collapsing improves how efficiently I achieve the required test coverage. With fewer vectors, I need to apply less test data to each chip. Shorter test sequences can improve the overall manufacturing testing throughput. Reducing the fault set also decreases the computational effort required by ATPG. Exhaustive testing means applying every possible combination of the circuit inputs. For n inputs, I would need 2 to the power n test vectors. This gives complete coverage of the possible input combinations. However, this becomes impractical when the circuit has more than roughly 20 to 25 inputs. The number of exhaustive test vectors increases exponentially as the input count increases. For n inputs, I need 2 to the power n vectors to cover every combination. With many inputs, that requirement quickly becomes too expensive to use. Fault-oriented methods avoid the need to exercise every possible input combination. Functional testing focuses on input combinations that represent valid states of the circuit. I apply combinations that correspond to the circuit's intended operations. Invalid input combinations are left out of the test set. Unused input combinations are also excluded. By excluding invalid states, I can reduce the number of required test vectors. This makes the resulting test set smaller than an exhaustive one. The testing effort is concentrated on meaningful circuit behavior. Functional testing is still different from explicitly targeting faults. Fault model-based testing creates vectors specifically for the faults remaining after collapsing. I combine the reduction from fault collapsing with targeted test generation. The testing effort is directed specifically toward detectable faults. This gives an efficient alternative to testing every possible input combination. After collapsing, the fault list contains only the representative faults that still need attention. I generate vectors specifically for those remaining faults. The resulting test set covers all detectable faults. At the same time, the number of required vectors is minimized while preserving coverage. Fault collapsing is a key method for making digital circuit testing more efficient. I reduce the number of test vectors without losing the ability to detect faults. Fault equivalence lets me remove faults that have identical detection behavior. Fault dominance lets me remove faults whose detection is already covered by stronger faults. Using these reductions, I can turn a very large fault set into a compact test suite. Equivalence and dominance give me systematic ways to reduce the fault list. The resulting tests still provide comprehensive coverage of the detectable faults. Overall, this makes practical test generation more efficient. Integrating these techniques into ATPG has significantly improved manufacturing test flows. I can achieve thorough fault coverage without requiring excessive testing time. Smaller test sets also help avoid unnecessarily high manufacturing test costs. As semiconductor circuits become more complex, efficient test generation becomes increasingly important. Future test automation can continue building on the principles of fault collapsing. Machine learning could be used to make test generation even more efficient. Statistical methods could also help improve the efficiency of generating tests. Deterministic fault models will continue to provide a rigorous foundation for coverage. I use fault equivalence to eliminate redundant faults that behave identically during detection. I use fault dominance to remove faults whose detection is already covered by another fault. I use checkpoint optimization to concentrate testing on important circuit locations. Together, these techniques give me smaller, efficient, and comprehensive test sets.